Thank you very much. It's really wonderful to be back here at ICTS. This institution is a dream come true for so many of us. And here's wishing it achieves even greater heights in the next 10 years. So I want to begin by wishing ICTS a very happy 10th birthday. Here's the obligatory picture with Spenta in hard hats at the construction site. This is a little bit further along than David's picture yesterday, so I don't look quite as skeptical. But really, just in the last 3 years, the way the campus has changed is really inspiring. And yeah, wishing it just greater heights in the next 10 years. It's really been amazing to watch what ICTS has done in its first decade. And it's been an honor for me to be affiliated with ICTS. So what I want to talk about today is the notion of a Squarefree number. This is a very fundamental notion in number theory. So it's a property of whole numbers, the property of being square-free. And so what does it mean to be square-free? Well, the name kind of explains it. So an integer or a whole number is called square-free if it has no repeated factor in its prime factorization. So when you break it up into prime factors, no prime occurs more than once. Or another way to say that is that a number is square-free if it's not divisible, evenly divisible by any square number other than 1, of course. So that's the origin of the term square-free. So for example, 2 is square-free, minus 6 is square-free, 42 is square-free, 42 is 2 times 3 times 7, right? All primes are distinct in its prime factorization, so those numbers are square-free. But if you look at 12, 12 is 2 times 2 times 3, 2 occurs twice, so it's not square-free, right? It's divisible by 4. Minus 18 is not square-free because it's divisible by 9. 50 is not square-free because it's divisible by 5 squared. Okay, so square-free is just a simple property of a number. You can test it just by dividing by all possible squares and make sure that it's not divisible by any square, or you can break it up into prime factors and just make sure that no prime in the prime factorization occurs more than once. Okay, so that's what it means to be square-free. It's a simple property of a whole number. And the first natural question that arises is if you pick a random whole number, how likely is it to be square-free? So what's the probability that a random integer is square-free? That's not a very precise question, because what does it mean to take a random integer? There are infinitely many integers. There's no natural probability distribution on a countable set, countable infinite set. But what we mean by it is, well, you can take all numbers up to, say, 1 million and ask what proportion of those are square-free. Then you take all numbers up to 1 billion and ask how many of those are square-free. And in general, you ask between all the way up to x, you ask for a big number x, how many of them are square-free, and then you let x go to infinity. And if that proportion approaches something, then that'll be considered the probability that a number is square-free. So more precisely, what we mean by probability that a random integer is square-free is we're asking what is the value of the limit as x goes to infinity of the count of all numbers between minus x and x that are square-free divided by the total number of numbers between minus x and x. Right? So this expression, the limit, is just the proportion of numbers that are square-free that have absolute value at most x, and then you let x go to infinity and you ask, does that limit exist? Okay, so that's what we mean by a probability of a number being square-free. And I already revealed the answer in my abstract, so there's no point in holding the suspense. The answer turns out to be 6 over pi squared. That's the probability. So 6 over pi squared is about 61%. So if you pick a random whole number, the probability is about 61% that the number is square-free. But more precisely, it's 6 over pi squared. And that's something that's always very intriguing to people not in number theory, because this is an instance where pi comes up, and there's no circle around, we're not measuring anything. Is this just a property of the whole numbers? And here in a natural way is coming pi, just by a simple number theory question. So in some sense, this is the number theoretic definition of pi. It's a very simple way of arriving at pi just by asking a simple question about whole numbers. So you might ask, well, why is it 6 over pi squared? And the other thing you might ask is, does this actually, so David was talking about the scientific method yesterday. Does the theoretical result agree with experiment? I consider that very important as well, even though I'm a mathematician. So what's the probability that a random integer is square free? What do experiments say about this? Well, if you look at the proportion of square free numbers up to 10, okay, what numbers are not square free up to 10? Well, 4 is not square free because it's a square. 8 and 9, right? Those numbers are not square free. Everything else is square free. So the 7 of the first 10 numbers are square free. So the proportion of square free numbers up to 10 is 0.7. Remember, the theoretical prediction was 61%. Okay, so it's kind of close already. If you count the number of square free numbers up to 100, you find that they're exactly 61. So already by 100, it's giving the exact right prediction. If you count up to 10 cubed, it's 0.608. Remember, the actual correct probability is 0.6079. 6 over pi squared is 0.6079. So here we're still at 0.608. But then by 10 to the 5, you're already at 0.6079. And then if you go up to 1 crore, 10 million, 0.60792, which is correct up to 5 decimal places. So already by 10 to the 7, you're correct up to 5 decimal places. Okay, so the theoretical result does agree very well with data. But now I want to explain why. So how does one arrive at this theoretical result? Why is the answer 6 over pi squared? And so I won't be able to give the whole proof of this, but I want to give a heuristic explanation. Why does 6 over pi squared come up as the answer? So, okay, well, suppose n is a random integer. So you just, okay, in the sense that we talked about before, you choose n between minus x and x, where x is huge uniformly. So suppose n is a random integer, chosen in some huge range. And you want to know what is the probability that it's square free. Okay, well, remember, n is square free if and only if it's not divisible by 4, by 9, by 16, by 25, and so on, right? But actually, you only need to look at the prime squareds. So as long as it's not divisible by 2 squared, 3 squared, 5 squared, 7 squared, 11 squared, and so on, then it's square free, and vice versa. So that's what it means to be square free. So to test whether a number is square free, you just have to test whether it's divisible by 2 squared, 3 squared, 5 squared, 7 squared, 11 squared, and so on. Okay, now what is the probability that a number is not divisible by, say, 2 squared? Well, what's the probability that it is divisible by 2 squared? 1 over 2 squared, right? 1 over 4. So in general, what is the probability that n is not divisible by p squared? Well, 1 over p squared of all numbers are divisible by p squared. So the probability that a number is not divisible by p squared is 1 minus 1 over p squared, right? Because every p squared number, every p squareth number is divisible by p squared. All the others are not. So the probability that you're not divisible by p squared is 1 minus 1 over p squared. Okay, so then what's the probability that n is not divisible by p squared for any of the primes? P equals 2, p equals 3, p equals 5, p equals 7. Well, that's just going to be 1 minus 1 over 2 squared. That's the probability that you're not divisible by 2 squared. Times 1 minus 1 over 3 squared. That's the probability that you're not divisible by 3 squared. Times 1 minus 1 over 5 squared. Times 1 minus 1 over 7 squared. And so on, forever. That's the heuristic part. So the assumption here is that the event that a number is divisible by 2 squared is independent of the event that a number is divisible by 3 squared. And so we're just multiplying the probabilities. And that's true for any finite number of primes. What's not obvious is that it's true even if you say this for all primes at once, okay, that they're all independent. So that's the heuristic assumption here, is that somehow all primes should behave independently, and so you should just be able to multiply all the probabilities, and that should give you the correct probability. Okay, so how do you evaluate this thing? So we all learn how to sum a geometric series. So the observation here is that 1 over 1 minus 1 over 2 squared is the answer to a question on how to sum a geometric series. So this geometric series here, how do you sum this? Right, the answer, right, the simple formula for this geometric series is just 1 over 1 minus 1 over 2 squared. So it's just the inverse of this. So usually in school we go the other way. We're given this geometric series and we say, oh, it's equal to that. But here we're going the other way. So 1 minus 1 over 2 squared, the reciprocal of that is just this geometric series here. So that's why we put a minus reciprocal here, and the same here, and so on. So basically we've written each of these as 1 over the sum of a geometric series. So that's the trick. And now, okay, we'll take the inverse out, and we'll just multiply all these geometric series together. And what happens when you just multiply it out completely? Well, it turns out you get exactly the sum of the reciprocal squares. And why is that? Well, okay, well, when you multiply 1 times 1 times 1 times 1 all the way, there's the 1. If you just take the 1 over 2 squared here, but take 1 in all the other factors, here's the 1 over 2 squared. Here's the 1 over 3 squared. You'll take a 1 in every other factor. The 1 over 4 squared will come right here. So the reason this is true is that you get the sum of the reciprocal squares is because of unique factorization. Every whole number is uniquely the product of powers of primes. So in other words, every square number is uniquely the power of even powers of primes. So if you multiply this all out, in the denominator you'll get every possible square exactly once. So this is using the fact that every whole number is uniquely decomposable into primes. And then that fact, how to sum the reciprocal squares, is a famous fact from Fourier series. If you expand the Fourier series of the function x squared between minus pi and pi, and then just plug in pi, you find that the sum of the reciprocal squares is pi squared over 6. And since we're taking inverse of everything, the answer should be 6 over pi squared. So that's why we expect the answer to be 6 over pi squared. So it basically comes from the fact that it's related to the sum of the reciprocal squares by this trick here. And so, well, the reason this is a heuristic proof is because we assume that all primes behave independently. Not some finite set of primes, for which it's true, but the fact that we just multiplied it over all primes. And that actually in general is not true. If you impose certain conditions modulo p, well, it's true here, but in general, if you impose conditions modulo infinitely many primes, you can suddenly arrive at the empty set. They're not necessarily independent in general, but in this case, they do turn out to be. So this heuristic proof can actually be made a proof, and that's what I want to note next. I won't give the actual proof, but I just want to note this heuristic proof can in fact be made a rigorous proof, and it's a classical result in analytic number theory. It's sort of the foundation of the area called sieve methods in analytic number theory. So I'll just say a couple sentences about how one goes about justifying this heuristic proof. To justify the heuristic, one has to actually do this for finitely many primes at a time, but more and more primes. So you'll take k primes and you'll ask it to be not divisible by the kth prime squared for the first k primes. And there it is true that the primes behave independently. So you get some kind of estimate that's close to 6 over pi squared, and what you have to show is that the error from 6 over pi squared is bounded in terms of k, and that bound goes to 0 as k goes to infinity. So you do this for finitely many primes at a time, but more and more, and at each step you have to estimate the error from the actual right answer. And you have to show that that error goes to 0. And the key ingredient in showing that the error goes to 0 is this simple property of the whole numbers that you're trying to sieve out those numbers that are multiples of p squared. And the nice property of the whole numbers is that multiples of p squared occur evenly in the whole numbers. They occur every p squared numbers, starting at 0. So you start at 0 as a multiple of p squared, and then all the other multiples of p squared come evenly every p squared numbers. seems like a trivial property, but this property will go away in a second when we ask a slight generalization of this question. But if you're just asking about the whole numbers, multiples of p squared are evenly spaced, and that can be used to estimate that error that you need to show goes to 0 when you make that heuristic proof in actual proof. And so this is an actual theorem proved rigorously that the proportion of numbers that are square free is actually equal to 6 over pi squared. Okay, so the next natural question that comes up for number theorists in studying square-free numbers is if you have a polynomial with whole number coefficients and you look at its values, what proportion of the values taken by the polynomial are square-free? That turns out to have many applications if we actually knew how to solve that problem in general. So the question precisely is, suppose you have a polynomial in, say, n variables with whole number coefficients. You can ask, what is the probability that a random value taken by f is square-free? And so again, you can make that precise in the same way. We're going to take x1 through xn. We're going to plug in values in a big box in n-dimensional space. And we're going to look at the proportion of values in that big box that are square-free. And then we'll let the size of that box go to infinity. And we'll ask, does that approach a limit? And if it does, we'll say that's the probability that a value of f is square-free. So in symbols, it's just we'll take the limit as x goes to infinity of the total count of numbers in that box, f applied to values in that box of size x, right? So we're going to take all the variables bounded by x, and we'll count the total number of values of f in that big box that are square-free, and we'll divide by the total number of values in that box, which is about x to the n, or 2x to the n. And we'll ask, as that box goes to infinity, the size of that box goes to infinity, what is that limit as x goes to infinity of that proportion? First of all, does that value even exist? And if it exists, then that will be called the probability that f takes square-free values at a random argument. So note that the original question about square-free whole numbers was the special case where f of x is equal to x. Right? If you look at the polynomial f of x equals x, and you plug in numbers 1 through n, you get exactly back the numbers 1 through n. And the conjectured answer is exactly computed as we did the case of 6 over pi squared. Namely, you look at the probability that the lambda p will denote the probability that the polynomial takes a value that's a multiple of p squared, and then we'll multiply it over all p, and that's going to be our conjectured answer. So the value of that limit should be a product of lambda sub p, where lambda sub p is the probability that the polynomial takes a multiple of p squared as its value. That's the conjectured answer. But in this case, it's an unsolved problem for a general polynomial. For degree 1 polynomials, as I said, that heuristic proof could be made rigorous, and it had to do with the fact that multiples of p squared occurred evenly in the whole numbers. But once you're a higher degree polynomial, where the multiples of p squared occur, they don't necessarily have to start at 0. It could start anywhere between 0 and p squared. And so that evenness starting at 0 is not the case. And that's where the proof breaks down in general. And so in general, for a general polynomial, this is an unsolved problem. And actually, in 2 minutes, I can tell you everything that's known about this problem because there's so little known. So what is known? Okay, so as I said, one variable polynomials are known. F of x equals x. That case, you get 6 over pi squared, as I said. Actually, degree 2 is also known, and the same method of proof, it just barely squeaks through. If you just take the proof for degree 1, apply it to degree 2, it just barely works. Degree 3 was unsolved for over a century while people were thinking about this. It was solved by Hooley in 1967, just a degree 3 case. And then for the last 50 years, people have been trying to understand anything higher than degree 3, even for a single polynomial. I'm not talking about all polynomials, just a single polynomial of degree bigger than 3. No one has ever been able to touch. So degree greater than or equal to 4 is completely unsolved. Actually, the situation is even worse than that. it's not even known, for example, if you just take the simplest degree 4 polynomial, I say x to the 4 plus 2. Not only is it not known what the probability is that it takes square free values, but it's not even known that this polynomial takes infinitely many square free values. You expect that it takes, positive with positive probability, you expect it to be taking square free values, and yet we don't even know that it takes infinitely many square free values. So it's just a simply stated problem. It's kind of embarrassing to the people in the subject, but we can't even say that it takes infinitely many values that are square free, even zero density. So we can't rule out that x to the 4 plus 2 at some point is only taking square full values. We can't rule that out. We can look at polynomials with more than one variable, and that can sometimes make things easier. So for example, if you look at homogeneous polynomials in 2 variables, then up to degree 6 were handled by Graves in 1992, 25 years ago. And that's the 2 variable case. Up to degree 6 has been handled. And that's essentially the last result in this subject. So degree greater than or equal to 7 in 2 variables, unsolved. So generally speaking, if the number of variables is huge, so if you have a polynomial in lots and lots of variables compared to the degree, then the circle method of Ramanujan and Hardy and Littlewood is applicable. So the only other case that's sort of understood by the work of Ramanujan and the follow-up work of Hardy and Littlewood is that if you have lots of variables compared to the degree, then you can actually prove the conjecture that the polynomial takes the correct density of square free values. And this really is all that's known on this problem. Some of you may have heard about the ABC conjecture. There's a lot of news about the ABC conjecture in the newspapers these days. It may have been proven. But it will take maybe decades for mathematicians to digest the proof of Shinichi Machizuki. But if the ABC conjecture is true, then actually this problem in one variable is solved. So the ABC, Granville and Lee and Ramamurthy showed that if the ABC conjecture is true, then the one variable case is true, that the correct density of square free values are taken by that one variable. So it's just another example. The ABC conjecture, when you read its statement, it's not so obvious to a number theorist why you would make such a statement, but it has very concrete applications. For example, it does tell you for one variable polynomials that a one variable polynomial takes the correct density of square free values. So the ABC conjecture is very powerful, even though it looks kind of hard to penetrate. It has very, very concrete applications, this being one of them. That for one variable polynomials, it does tell you the correct density of square free values. So in particular, it not only tells you that x to the 4 plus 2 takes infinitely many square free values, but it tells you the exact proportion of values that are square free. For higher degree polynomials, for polynomials with more than one variable, actually even the ABC conjecture, people have not been able to use that to get the correct density. So for polynomials in more than one variable, with some other kind of weird way of ordering, Poonen showed that ABC conjecture does imply the correct density, but it's with a different kind of ordering. It's not taking it in a box and getting bigger and bigger. It's doing something more complicated. So for multivariable polynomials, it's not known, even assuming the ABC conjecture, that the correct density of square free values are taken by a multivariable polynomial. Okay, so that's the state of knowledge about the problem. So I'll just mention one recent result that does handle one additional case that's been sort of important for number theorists for many years. So many natural polynomials whose square free values are needed do not fall into any of these known categories that I just mentioned, because there are very few known categories. And one important example is the discriminant of a polynomial of degree n. So if you have a degree n polynomial, there's a notion of discriminant of the polynomial. We all learn it for quadratic polynomials. So if you have ax squared plus bx plus c, a, b, c are the variables that are parameterizing your degree 2 polynomials. And the discriminant of that is this. Well, from that, if you take the discriminant of a polynomial, it's itself a polynomial in the coefficients. And it's this expression we all learn, b squared minus 4ac. That's the discriminant of a degree 2 polynomial. And that school children are all taught, that polynomial. But once you go to degree 3 polynomials, for some reason we're never told what it is, what the discriminant of a degree 3 polynomial is. The reason is it's a little bit long, but it fits in one line. Discriminant of a degree 3 polynomial is this degree 4 expression here in 4 variables. And in general, if you look at the discriminant of a degree n polynomial, it's a polynomial of degree 2n minus 2 in n plus 1 variables. And it's been a long time open problem to understand for these polynomials. These are multivariable polynomials in 3 variables, and 4 variables, and 5 variables, and so on. And it's been a long time open question. What is the density of square-free values taken by a discriminant polynomial? So this sequence of polynomials. And it's been a long time unknown, but it has many applications in algebraic number theory if we were to know that. And so that's the result I want to announce today, is that we can actually work out what the density of square-free values are for discriminant polynomials, which didn't fall into any of the known categories before. So if you take the discriminant polynomial of a degree n polynomial, the density of values that are square-free exists and is equal to that conjectured constant that we talked about before. And so these conjectured values, it turns out they approach about 35% very quickly with n. So these constants actually approach a constant rho as n goes to infinity, and that's approximately 0.35. So if you take a random large degree polynomial over the whole numbers, and you compute its discriminant, it's about 35% probability that that discriminant will be square-free. And the method behind the proof actually uses group theory. It uses the fact that these polynomials are invariant by a certain action of SL2Z, and that special symmetry is what's used to arrive at the result. That method has actually turned out to have lots of other applications, in particular about the distributions of number fields and about ranks of abelian varieties. But it's cool that that method actually has an application to something very concrete, the density of square-free values taken by a particular polynomial. And in particular, it has applications to this very classical problem that involves the number theoretic definition of pi. So, okay, so I'll stop there. Thank you so much for your attention.
Okay, thank you, Manjul. It was hard to interrupt you because it's so interesting, so I decided to give you a few seconds.
Oh, thank you.
Okay, so I'm sure there are many questions in the audience.
Have you tested this experimentally?
I have. You always must do that. That's right. Okay. Yeah. Yeah, it agrees very well with the data. So actually, you just make, even if by degree 10 polynomials, just pick random degree 10 polynomials, and you test how often they're square-free, and it's 35% very quickly. Yeah. This particular number doesn't, but there's actually, I kind of tweaked the question that number theorists are interested in about polynomials. So number theorists like to study what are called number fields, which are extensions of the rational numbers, where you adjoin a root of a polynomial. So inside the rational numbers, there's a notion of integer, which are the usual integers. Inside these bigger fields, there's also notions of integers. What are the integers in that bigger field? And the computation of integers in those bigger fields is is generally tough. But for certain polynomials, including those that have square-free discriminant, it's very easy to compute the ring of integers in those bigger number fields. So there's a natural way of taking a polynomial. You adjoin its root, you get a number field, and if you adjoin a root to the integers, you get some bigger ring of integers. When is that the full ring of integers of the whole number field? That's a question you can ask for each degree n polynomial. And the answer, the probability that the polynomial always gives you the correct ring of integers is 6 over pi squared for every n, independent of n. So that natural question that number theorists would ask, square-free is just a special case, but if you just generalize that question about how often can you easily compute the ring of integers of a number field, the answer turns out to be 6 over pi squared in every degree n. And the n equals 2 case turns out to reduce to the usual square-free numbers problem. So there is a sense in which this has to do, these all have to do with pi.
I have a follow-up question on the experiments. Do you have a theory about your experiments? So in other words, you know about the finite size scaling? Do you know how fast even the 6 over pi squared gets, do we know asymptotically if you go up to n, what the corrections are?
Right, right. So there are conjectured correction terms that agree very, very well with the data. And the best known correction terms give you about x to a smaller power. So the total number of integers up to x that are square free is 6 over pi squared times x plus x to a strictly smaller power. So that means the convergence is going to be pretty quick. And the best second term, I don't remember the precise exponent, but it uses the Riemann hypothesis. So it's neat how this problem connects to the Riemann hypothesis, it connects to the ABC conjecture. If we knew the Riemann hypothesis and the ABC conjecture, we'd have very good main terms and error terms. The main term would come from the ABC conjecture, the second term would come from the Riemann hypothesis. It's neat how this simple problem connects to two of the major problems in number theory.
Are we allowed to run over, or is the time strict? Okay, maybe we do one more question.
I just had a quick question. Same heuristic that that you had also says that 6 over pi squared is the probability that two integers are relatively prime.
That's right.
Is there an analog of that for the polynomials?
Yeah. You can formulate analogs of that as well. You can take two different polynomials and take random values of the two and ask.
Is it the same probability?
Oh no, it changes a little bit. Yeah, but because it depends on the polynomials. It depends on the two polynomials. Yeah.
Okay,
Yeah,
let's thank Manjul again.
Thanks so much.
Thank you very much.